The fate of the universe has fascinated scientists and the public for millennia. Imagine a cosmos where every star, galaxy, and even space-time itself moves toward an inevitable conclusion. This section explores how the universe might end, not through a sudden cataclysm, but as a gradual, unavoidable outcome shaped by the fundamental laws of physics. From the relentless rise of entropy to the mysterious influence of dark energy, modern cosmology offers a range of scenarios that challenge our understanding of time, space, and matter. Will the universe fade into a cold, dark void or unravel in a violent upheaval? By examining its past and projected future, we lay the foundation for understanding the ultimate fate of everything that exists. The ultimate question: how will the universe end? Picture yourself beneath a starry night sky, where every star is a witness to the universe's amazing and ever-changing past. A deep question arises at that moment. How will the cosmos, with all its complexity and beauty, ultimately end? This isn't just some abstract thought. It's a major scientific question that calls into question everything we thought we knew about the rules of space, time, and energy. You have to realize that the world is not set. It is a living, changing thing. Since its powerful start in the Big Bang, the universe has been growing, cooling, and building things, from tiny particles to galaxies and groups of galaxies. The universe gets ready for the next part of its growth with each new time. As we look deeper into space and time, we have to face the fact that things will always be changing, both in the form of new things being made and old things falling apart. One popular idea is heat death, in which the universe slowly moves toward a state of maximum entropy. In this case, all the energy available is spread out evenly. All processes stop, and the universe settles into a cold, dark space with no meaningful activity. This kind of end is not sudden, but the end of an endless decline, where the dancing of stars and galaxies slowly fades into uniformity. On the other hand, some ideas promise more dramatic outcomes. For example, the Big Rip theory says that if dark energy keeps speeding up the expansion of the universe, it might finally be stronger than all the forces of gravity. In this scenario, everything in the universe would be ripped apart in a final, violent breakdown, from planets to atoms. On the other hand, the thought of vacuum decay says that the universe might be in a brief false vacuum that could quickly change to a lower energy state, which would completely change the laws of physics. There is also the possibility that gravitational forces might one day reverse the current trend of expansion, leading to a big crunch, in which the universe collapses back into a dense state, possibly setting the stage for a new cosmic cycle. Other models, such as Cyclic or bouncing universes, propose that the cosmos undergoes endless cycles of birth, evolution, and rebirth, where endings are merely transitions to new beginnings. Setting the stage, defining the end of everything. It is important to be clear about what we mean by the end of everything from a scientific point of view before we look at the different scenarios that could mean the end of the universe. Unlike the dramatic endings that are common in literature, the end of the world doesn't have to happen quickly or badly. Instead, it is a slow process that is controlled by the basic rules of physics and takes astronomically long times to complete. In this section, we explain the main ideas that help us understand the end of the universe, such as entropy, cosmic expansion, and the interaction between matter and energy. We also go over the main theories that explain how the universe might stop supporting the changing processes that make it what it is now. Entropy, a measure of disorder or unpredictability, is crucial to the notion that the cosmos is ending. The second law of thermodynamics states that entropy tends to rise with time in any closed system. This implies that energy will become more evenly spread across the cosmos over billions of years, until there are no more notable variations to propel activities like matter migration, chemical reactions, or star formation. The term heat death or the big freeze are frequently used to describe this slow decrease toward a state of maximum entropy. In this scenario, all of the energy that formerly drove the stars and galaxies is so uniformly distributed that the universe gradually and irrevocably fades away, leaving behind a cold, black void where nothing significant occurs. But entropy is simply one aspect of the meaning of the end of the cosmos. Additionally, contemporary cosmology informs us that the universe destiny is closely related to its rate of expansion. Dark energy, an enigmatic force that makes up around 70% of the universe's total energy density, is responsible for this acceleration. There are several conceivable results when cosmic expansion is influenced by dark energy. For example, the universe may be headed toward the big freeze scenario, in which galaxies rapidly separate from one another, leaving the universe chilly and isolated, if dark energy stays constant or rises over time. On the other hand, the Big Rip, a situation where the accelerated expansion is so severe that it finally rips apart galaxies, stars, and even atoms, might result from dark energy expanding unchecked. Another theoretical possibility is that our current state of the universe represents a metastable condition, a false vacuum. In quantum field theory, a false vacuum is a temporary state that could eventually decay into a more stable, lower energy, true vacuum through a process known as vacuum decay. Should such a decay occur, it would propagate at the speed of light, instantaneously altering the fundamental constants and laws of physics throughout the universe. This sudden transition could render all known structures and forms of matter unrecognizable, effectively ending the universe as we understand it, even though a new stable state might emerge afterward. While these models, heat death, the Big Rip, and vacuum decay, offer distinct visions of cosmic endings, they also illustrate that the concept of an end is not necessarily synonymous with total annihilation. In the Big Freeze, for instance, the universe doesn't vanish. Rather, it reaches a state where no work or significant change can occur. In the case of vacuum decay, the transition would be abrupt and transformative, but it might simply mark the beginning of an entirely different cosmic regime. Similarly, models such as the Big Crunch or Cyclic universes propose that the universe could eventually reverse its expansion and collapse back into a dense state, potentially igniting a new cycle of cosmic evolution, a rebirth rather than a definitive end. The timescales involved must also be taken into account when defining the end of the cosmos. The scale of cosmic processes is significantly larger than that of human lives. Over billions or perhaps trillions of years, things like the universe's slow cooling or the possible disintegration of a false vacuum are expected to take place. The asymptotic future, in which the dynamic processes that now support cosmic structures slow to a near stop, is what scientists frequently mean when they talk of the universe ending. It is a state of ultimate equilibrium, in which there are no longer any energy differentials required for additional evolution. And the cosmos remains a static, unchanging background. These definitions are deeply intertwined with our understanding of the fundamental forces and particles that govern the cosmos. The interplay between gravity, electromagnetic forces, and the strong and weak nuclear interactions determines not only the structure and evolution of galaxies and stars, but also the mechanisms by which energy is transformed and dissipated over time. Any comprehensive model of the universe's end must account for these interactions and explain how they evolve as the cosmos expands and cools. For example, in the heat death scenario, the gradual increase in entropy is directly linked to the dissipation of energy that initially drove star formation and other energetic processes. As energy differences vanish, the forces that hold structures together become ineffective, leading to a universe that is essentially frozen in its final state. Cosmic structure formation and the role of gravity. Gravity has been the builder of the great architecture of the cosmos from the first seconds following the Big Bang. Following the Big Bang, the cosmos was almost homogeneous, hot, dense plasma with minute density imprints left by quantum events during cosmic inflation. These minute differences, on the scale of 1 part in 100,000, were the seeds from which all cosmic structure would finally flourish. Gravity operated on these oscillations throughout billions of years, progressively dragging stuff together to create the first stars, galaxies and clusters, and finally weaved the complex cosmic web defining our planet now. In the very beginning of time, the universe was a rough, growing sea of particles and radiation. Neutral hydrogen was made when protons and electrons came together as it cooled. This made the world clear to light. This process, called recombination, left behind a trace of radiation called the cosmic microwave background. This background radiation still gives the universe a soft glow. There are faint traces of the initial changes in density left behind in this leftover radiation. Even though they were hard to notice, these changes were enough to make gravity work. Even a little more dense areas had a slightly stronger gravity pull that pulled in more matter from the surrounding areas. Over time, this process that got out of hand created gravity wells, which got deeper as more matter fell into them. As these gravity wells got bigger, the first stars were born inside them. In the thick centers of these areas, gas clouds fell apart under their own weight, which started nuclear fusion and lit the first stars on fire. In turn, these stars lit up their surroundings and started the process of reionization, which cleared the early universe of the cosmic dust that had been covering it. The light from these first stars not only marked the start of the dawn of the universe, but it also gave us the energy to build even more structures. As stars clumped together, they made the first galaxies, which were small sphere groups that would later grow into more complex systems. Gravity, acting as a sculptor, continued to shape these early galaxies through mergers and accretions. Over time, the gravitational attraction between neighboring galaxies led to collisions that merged smaller systems into larger, more massive galaxies. These interactions were not gentle. They often triggered bursts of star formation as the colliding gas clouds compressed and cooled, igniting new rounds of stellar birth. The chaotic dance of merging galaxies eventually gave rise to the majestic spiral and elliptical galaxies we observe today. The process of building up cosmic structures is not limited to galaxies. On a bigger scale, gravity arranges matter into a huge web of strands, groups, and huge empty spaces. There isn't a random distribution of galaxies and galaxy clusters in the universe. Instead, they form along thick, thread-like structures that span hundreds of millions of light years and connect to each other. These filaments are like roads for matter, and groups are fed at their connections. The creation of this network, which is one of the most interesting things about the big universe, is due to the interaction between gravitational pull and the original changes in density. Deep sky surveys and redshift readings, which show how galaxies are spread out in 3 dimensions, are pieces of proof for this cosmic web. Large telescopes have made very detailed maps of parts of the universe. These maps show that galaxies are grouped together in a way that matches what models of gravity and stability say should happen. These studies have not only shown that gravity does play a part in shaping the structure of the universe, but they have also helped scientists measure important things like the rate of growth and the distribution of mass on a cosmic scale. Moreover, gravitational lensing, where the light from distant galaxies is bent by the gravitational field of intervening matter, provides a unique window into the unseen mass that structures the universe. By studying how light is deflected around massive clusters and filaments, scientists can infer the distribution of mass in these regions, further underscoring the dominant role of gravity in the cosmic landscape. These lensing effects not only help map the visible structures, but also reveal the underlying gravitational scaffolding that guides the formation and evolution of the entire universe. As time goes on in the universe, the structures that gravity has built keep changing. The future will be full of changes because of how gravity and the growth of the world work together. Galaxies are moving apart because of the general growth, while gravity pulls matter together. The way these forces interact has shaped the development of cosmic structures and will eventually decide the final fate of the universe. In the far future, gravitational effects could slow the growth in some areas, which could cause groups to merge or superstructures to form. If, on the other hand, expansion is stronger than gravity pull, cosmic structures may eventually become isolated islands in a world that is expanding faster and faster. In studying the evolution of cosmic structure, scientists not only gain insight into the history of the universe, but also refine models that predict its ultimate fate. The same gravitational processes that formed galaxies and clusters are intimately linked with scenarios for the universe's end, whether it be a gradual cooling as structures dissolve into a homogeneous state, or a dramatic reconfiguration of matter and energy. The continuous cycle of formation, interaction, and eventual decay is a testament to gravity's relentless influence. Cosmic collisions and mergers, the dynamical evolution of galaxies. As galaxies formed from the gravitational collapse of primordial gas, they did not evolve in isolation. Instead, their mutual gravitational attractions often led them to collide and merge, initiating transformative processes that reshaped their morphology and triggered intense bursts of star formation. When two galaxies approach one another, their gravitational fields interact, distorting their shapes and creating tidal tails, streams of stars and gas that are pulled out from the main bodies. These dramatic features serve as cosmic signatures of past collisions and provide vital clues about the dynamics of the interacting systems. When the Milky Way and the Andromeda Galaxy are merging, it's one of the most well-known cases of galaxies crashing into each other. There are still millions of light years between these two galaxies, but they are expected to crash into each other in about 4 billion years, which will drastically change the structure of both. Simulations show that when they join, the new galaxy might look like an elliptical galaxy instead of the spiral shape that we are used to seeing in galaxies. This change isn't just for looks. The merger will probably start waves of star formation as the gas clouds meet and squeeze together, lighting up the joining system for a short time. When galaxies join, a lot of important things happen. The first thing these crashes do is mix up the groups of stars and move metals, elements heavier than helium, around the galaxies. This chemical increase is very important for making planets and, by extension, for life to be able to grow in stars that come after this one. Second, mergers can push gas toward the center of galaxies, where it can feed supermassive black holes and maybe even start active galactic nuclei. The strong radiation and energetic streams that come with these events can change how fast stars form and how the home galaxy changes over time. There is a lot of proof from observations that the universe is colliding. Beautiful pictures of galaxies colliding have been taken by telescopes across the electromagnetic spectrum. These pictures include the amazing tidal tails of the antennae galaxies and the twisted structures of the mice galaxies. These data not only show that the dynamic processes are real, but they also let scientists study the specifics of how gravitational forces change the shape of galaxies over time. By using thorough spectroscopy and imaging, scientists can find out how fast the stars are moving and what they are made of in these systems that are meeting. This helps them figure out what happened to get them to where they are now. Cosmic collisions are not limited to pairwise galaxy mergers. In dense environments like galaxy clusters, multiple galaxies can interact simultaneously, leading to complex dynamical behaviors. These environments, where gravitational interactions are especially intense, can give rise to phenomena such as galaxy harassment, a process in which repeated high-speed encounters strip gas from galaxies and alter their morphologies. Over time, These interactions can transform spiral galaxies into elliptical or lenticular galaxies, fundamentally altering the population mix within clusters. In the hierarchical model of structure creation, small systems join to make bigger ones. This is where merging galaxies is very important. Computer studies that show how cosmic formations are put together by gravity help this bottom-up process. The simulations show that over billions of years, smaller galaxies keep merging into bigger ones. This creates the growth of huge elliptical galaxies and the complex cosmic web that makes up the universe's structure on a large scale. The distribution of dark matter is also affected by mergers, in addition to the visible stars and gas. Interactions and overlapping of the dark matter halos surrounding colliding galaxies are seen. Gravitational lensing investigations allow us to track the gravitational impact of dark matter, even though it does not produce light. These findings show that the merger process causes dark matter to be reconfigured in a complicated way, which further affects the dynamics of the newly formed galaxy. Cosmic radiation and its long-term impact on matter. Cosmic radiation is an energy field that is always present in the universe. It is very important to the long-term growth of the universe and shapes the way matter behaves on both small and large scales. This radiation comes from many different types of stellar events, ranging from the cosmic microwave background, which is low energy, to supernova and active galactic nuclei, which are high energy bursts. Over very long periods of time, cosmic radiation has an effect on the physical, chemical, and even biological processes that run the world. Cosmic radiation, at its most basic level, is made up of charged particles that move through space very quickly, mostly protons, atomic nuclei, and electrons. Several things, like the shock waves from supernova blasts, the turbulent areas around black holes, and the interactions in the cosmic medium, speed up these particles. Besides these charged particles, the radiation field is also made up of photons with a lot of energy, like gamma rays and X-rays. All of these parts work together to make a complicated radiation environment that changes everything from the smallest particles to the structure of galaxies. The interstellar and intergalactic medium is one of the most important things that cosmic energy changes. Cosmic rays and high-energy photons move through space and mix with dust and gas, which makes atoms charged and starts chemical reactions. These interactions are very important for making chemicals, some of which are necessary for life. As an example, cosmic rays can cause complex organic molecules to form in thick molecular clouds. This could provide the building blocks for life in areas where stars are forming. But cosmic radiation is like a double-edged sword. Too much of it can break down molecules and mess up delicate biological systems, but it can also start chemical reactions. The long-term exposure to cosmic radiation has critical implications for the stability of matter in the universe. Over billions or even trillions of years, the relentless bombardment by high-energy particles can lead to the gradual degradation of complex structures. In regions with intense radiation, such as near active galactic nuclei or within starburst galaxies, cosmic rays may accelerate the process of matter decay, contributing to the eventual dissipation of energy that drives dynamic processes in the universe. This gradual erosion of structure is a key component in scenarios like the heat death, where over immense timescales, energy becomes so uniformly distributed that no further work can be performed. Cosmological radiation is closely linked to how galaxies change over time. Cosmic rays are always present in galaxy clusters, and they can change the temperature balance of the medium inside the cluster. This can change how fast gas cools down and condenses to make new stars. Cosmic radiation can heat up some areas and stop gravity collapse in others. This controls the birth of stars and changes the way galaxies evolve. This interaction between warmth and cooling is important for understanding how galaxies die and come back to life, as well as how energy moves around in the universe as a whole. Astrophysicists use the marks that cosmic radiation makes to figure out what is going on in the universe. For example, the scattered gamma-ray background tells us about the high-energy processes that are going on all over the universe. Similarly, the range and strength of cosmic rays that are recorded close to Earth are affected by both nearby sources, such as the remains of supernovae, and the larger cosmic environment. Scientists can figure out the past of energetic events in the universe and learn more about the processes that help the universe evolve by looking at these signs. Apart from its direct effect on matter, cosmic radiation contributes to the larger cosmological setting by affecting the behavior of basic particles. Through processes like photopion generation, high-energy cosmic rays interacting with the cosmic microwave background can generate secondary particles. These interactions not only define the energy spectrum of cosmic rays, but also offer a testing ground for particle physics at conditions challenging for reproduction on Earth. This study offers insights on how matter behaves at the greatest energies and over the longest timescales, therefore revealing novel physics outside the standard model. The mix between radiation and matter will change as the cosmos ages. Radiation dominated the early cosmos, but as it grew, matter progressively became the most important factor controlling structure. But the density of stuff and radiation will lessen as cosmic expansion keeps on. Under conditions like the Big Freeze, cosmic radiation will finally be the major source of energy left. All other kinds of dynamic action will stop. The path toward a radiation-dominated state in the far future emphasizes the long-term influence of cosmic radiation on the fate of the universe. Heat death, Big Freeze, the gradual cooling of the universe. According to the heat death scenario, often known as the Big Freeze, the universe will eventually chill and homogenize due to the unstoppable rise in entropy. The second rule of thermodynamics, which asserts that entropy, or the measure of disorder, tends to rise with time in a closed system, provides a logical basis for this concept. This implies that over cosmic durations, the energy available to do labor gets more diffuse until there are no longer any notable gradients to propel activities like chemical reactions or star formation. At the beginning of the universe, shortly after the Big Bang, the cosmos was an extremely hot and dense plasma, a seething cauldron where energy was concentrated in a highly ordered state. As the universe expanded, it cooled, allowing the formation of subatomic particles and eventually atoms. This cooling process set the stage for the emergence of stars, galaxies, and all complex structures. However, this same expansion also means that the energy density decreases over time. Eventually, the universe will reach a point where the temperature becomes so low that no macroscopic processes can occur. You can think of the universe as a huge storehouse of energy that gets spread out equally over time. In the beginning, the high temperature and density made it possible for fast-moving processes like nuclear fusion in stars, the creation of complex molecules, and the gravitational clumping of matter. But as the universe keeps growing, galaxies get farther apart and stars run out of nuclear fuel. Not being able to use fusion to make a lot of new energy will cause stars to slowly die out, and their light will dim. Over many trillions of years, the universe will turn into a cold, dark place where only white dwarfs, neutron stars, black holes, and other degenerate objects will survive, slowly giving off their heat. The concept of entropy is central to understanding heat death. Entropy, in a thermodynamic sense, measures the number of microscopic configurations that correspond to a macroscopic state. When entropy is low, the system is highly ordered. When entropy is high, the system is disordered. In the current universe, we observe regions of low entropy where energy is concentrated, such as stars and galaxies. But these are local exceptions in an otherwise high entropy cosmos. Over vast timescales, The processes that maintain these low entropy regions, like nuclear fusion in stars, will cease, and the universe will evolve towards a state of maximum entropy. At that point, the temperature throughout the cosmos will approach absolute zero, and no thermodynamic free energy will be available to sustain motion or life. Mathematically, if we consider the universe as a thermodynamic system, its total entropy SSSS increases monotonically with time. The second law of thermodynamics can be expressed as delta S is greater than or equal to zero, or the change in entropy is greater than or equal to zero, indicating that any spontaneous process in the universe results in an increase in entropy. In an ever-expanding universe, this means that the available energy becomes more evenly distributed, and temperature gradients, necessary for the performance of work, diminish. As energy differences vanish, the ability of the universe to support processes that lead to complexity and life also disappears. The redshift of light from faraway galaxies is observational proof that the universe is growing all the time. Light's wavelength gets longer as the world grows, moving toward the red part of the spectrum. This redshift is a direct sign of how far apart galaxies are getting over time. Along with the finding that the expansion is speeding up due to dark energy, this paints a picture of a universe that will keep growing forever. In this case, the energy density keeps going down, which brings the universe closer to a state of temperature balance, which is a sign of heat death. One thing that happens in the heat death situation is that all processes stop, even ones that are necessary for life. Once the energy is spread out evenly, chemical processes that depend on energy differences will no longer happen. Once the intergalactic medium is too thin to cause gravity collapse, stars, which are what make the universe grow, will stop forming. Black holes, which take in matter and energy and store them in space, will finally disappear over very long periods of time due to a process called Hawking radiation. There will be less room for any kind of structure or action in the world as black holes lose mass. Critics of the heat death model sometimes point to the possibility of fluctuations in entropy that might, in theory, create temporary pockets of low entropy. However, according to the statistical interpretation of thermodynamics, the probability of such fluctuations leading to a resurgence of complexity in a universe that is overwhelmingly high in entropy is vanishingly small. In essence, while local decreases in entropy are possible on small scales, they are statistically insignificant when considering the fate of the entire universe. The concept of heat death extends our understanding of time to unfathomable scales. Current estimates suggest that the universe may reach a state of maximum entropy in an inconceivably vast timescale, a timescale so vast that it defies human intuition. On such a scale, the processes that currently define our universe would be replaced by a static, unchanging expanse where nothing of note occurs. The beauty and melancholy of the heat death scenario lies in its portrayal of the universe as a system that gradually loses its capacity for change, culminating in a final, almost serene equilibrium. The Big Rip: Dark Energy's Role in Dismantling Cosmic Structures. The Big Rip scenario paints a dramatic and terrible picture of the future of the universe. In this scenario, dark energy speeds up the expansion of the universe until it becomes so strong that it breaks through all natural barriers. In this case, the dark energy-caused pushback force doesn't stay the same. It gets stronger over time, breaking galaxies, stars, planets, and even atomic structures apart. At present, dark energy is thought to constitute about 70% of the universe's total energy density and is responsible for the observed acceleration of cosmic expansion. Its exact nature remains one of the most profound mysteries in astrophysics. However, theoretical models suggest that if dark energy behaves in a way that causes its density to grow without bound, then its repulsive effect could intensify to a point where it disassembles all forms of gravitationally bound structures. Initially, This would lead to the disintegration of galaxy clusters as the space between individual galaxies expands at an ever-increasing pace. Galaxies themselves would soon lose their cohesion, with stars being pulled away from their orbits, ultimately leading to the breakdown of the galactic structure. Even the forces that hold stars together in galaxies would fail as dark energy's power grows. In the last few steps of the Big Rip, the pulling forces at the level of solar systems, and finally even atoms, would be too weak to hold things together. Atoms would be torn apart because the electromagnetic force, which usually holds electrons to nuclei, would no longer be able to stop the growth from getting faster. People think that the Big Rip happens in a certain order. First, big structures break apart, then smaller systems, and finally, subatomic particles are torn apart. Mathematically, the Big Rip scenario is often modelled by a scale factor that diverges at a finite time in the future. The Friedmann equations, which govern the expansion of the universe, indicate that if the equation of state for dark energy falls below a critical threshold, the expansion becomes super exponential. This condition, known as phantom energy, means that the energy density increases as the universe expands, leading to a runaway effect. The time remaining until the Big Rip can be estimated based on the value of W. The closer it is to a critical threshold, the longer the universe will continue to evolve before reaching this catastrophic state. However, if W drops significantly below this point, the end could arrive relatively quickly on cosmic timescales. Observational evidence for dark energy comes primarily from studies of distant type IR supernovae and measurements of the cosmic microwave background, or CMB. These observations have firmly established that the universe's expansion is accelerating. Yet whether dark energy will continue to behave in a manner consistent with a cosmological constant or evolve into a phantom energy scenario remains an open question. Future observations, particularly those that can track the behaviour of dark energy over time, will be crucial in determining if the Big Rip is a plausible outcome. The Big Rip's certain onset once dark energy reaches a runaway phase is one of its most terrifying features. The Big Rip is characterized by the sudden and dramatic collapse of all cosmos structures, in contrast to the Big Crunch and heat death, which rely on reversal of expansion or gradual asymptotic fading, respectively. It is common to show the Big Rip as occurring in stages. First, clusters and galaxies start to separate billions of years before the end. Second, galaxies begin to unravel hundreds of millions of years later. And finally, in the last moments, the ever-accelerating expansion tears even atoms and nuclei apart. The Big Rip situation makes us think about what the universe's physical forces can and can't do. There would be no more known structures in the universe long before the rip happens if dark energy really does get stronger over time. This changes not only what happens to galaxies and stars, but also what happens to the basic building blocks of matter. The fact that matter can break down at such a basic level makes me wonder if physical rules are always true. It questions the idea that the world will always have the same particles and forces. Instead, it suggests that, in the end, even the basic building blocks of reality may be completely different. In theoretical talks, the Big Rip is sometimes compared to other possible outcomes, such as vacuum decay, where a quick change in phase could drastically alter the rules of physics without necessarily breaking structures down gradually. The Big Rip is especially dramatic, though, because it moves forward and covers everything. As dark energy makes space expand faster and faster, the idea of distance loses all meaning. Because space-time is stretched so far, the usual ideas of closeness and farthest distance are no longer useful. Critics of the Big Rip model argue that current observations have yet to provide conclusive evidence for the conditions necessary to trigger it. If future measurements reveal that W is at or just above a critical threshold, the universe might avoid the catastrophic fate of a Big Rip, instead approaching a more gradual and static end. Nonetheless, the possibility of a Big Rip remains one of the most compelling and terrifying visions of the universe's future. It encapsulates the profound impact that dark energy, one of the most mysterious components of the cosmos, could have on the ultimate destiny of all matter and energy. Vacuum decay, a quantum bubble triggering a phase transition. Based on the ideas behind quantum field theory, vacuum decay is a dramatic and possibly disastrous event that can happen. At its core, the idea of vacuum decay questions the idea that the state of space called vacuum, which has the lowest energy, is always steady. It instead says that our universe might be in a false vacuum right now, which is a metastable state that is not the real ground state. A small change or quantum shift could cause a phase transition in this case. This would cause a fast and permanent change in the universe's basic features. The notion of a false vacuum originates from the idea that the vacuum of space is not empty, but rather teems with energy. According to quantum field theory, even what we consider empty space has a baseline energy known as vacuum energy. In certain models, this energy landscape features multiple minima, local minima, false vacua, and a global minimum, true vacuum. Our universe could be residing in one of these false vacua, where the energy is higher than that of the true vacuum. While the false vacuum may appear stable over cosmological timescales, it is inherently unstable because quantum tunneling could eventually allow a transition to the true vacuum. Quantum tunneling is a phenomenon in which a system transitions between states that, according to classical physics, would be forbidden due to an energy barrier. In the context of vacuum decay, quantum tunneling could lead to the spontaneous formation of a bubble of true vacuum within the false vacuum. Once nucleated, this bubble would expand at the speed of light, converting the surrounding false vacuum into the new, lower energy, true vacuum. The process is analogous to boiling water, where bubbles of vapor form and expand in a superheated liquid. However, in the case of vacuum decay, the phase transition is far more drastic. The fundamental constants, particle masses, and even the forces of nature could be altered as the bubble expands, effectively rewriting the rules of physics as it passes. The potential consequences of such a vacuum decay are both profound and unsettling. If a bubble of true vacuum were to form, its expansion would not be confined by the usual limitations of space and time. Rather, it would engulf the universe at the speed of light. Everything within the bubble, galaxies, stars, planets, and even atoms, would suddenly find itself in a radically different physical regime. The laws of physics that govern the behavior of matter and energy in our current universe would no longer apply, rendering life and any existing structures unrecognizable. In essence, vacuum decay represents an abrupt and total transformation of the cosmos, a cosmic phase change that would effectively mark the end of the universe as we know it. Mathematically, vacuum decay can be described using the formalism of quantum field theory. The probability of a false vacuum decaying into a true vacuum through quantum tunneling is typically given by an expression of the formula gamma is approximately equal to A times E raised to the power of negative b over h bar. Where gamma is the decay rate per unit volume, AAA is a prefactor related to the details of the potential barrier. B is the action associated with the tunneling process, and h bar is the reduced Planck constant. Because the exponent is typically very large, the decay rate becomes extremely small, suggesting that our false vacuum could persist for billions or even trillions of years. However, even an incredibly small probability is significant when considering the vast volume of the universe and the immense timescales involved. In practice, it is hard to find signs of an approaching vacuum decay because the process would happen instantly and without any notice. There wouldn't be any slow building or warning signs that could be seen a long time in advance. The true vacuum bubble would expand so rapidly that it would engulf any observer before they could perceive or record any changes once the tunneling event occurs. Because of this, vacuum decay is still just a theory and not a real threat right now. based on what we know now. The cosmological constant and the energy density of the vacuum are both important ideas in the study of vacuum decay. The cosmological constant shows how densely charged empty space is in many cosmic theories. If the vacuum in our universe is really a fake one, then the cosmological constant we measure is not the very lowest value, but a higher value that can change over time. The main goal of both theory study and high-precision cosmological measurements, like those of the cosmic microwave background and large-scale structure, is to find out if this is true. The Big Crunch. Could the universe collapse back in? The Big Crunch shows a different picture of what will happen to the universe in the end. The current growth will stop and turn around, causing all matter and energy to fall back into a dense, hot state. In contrast to the ideas of slow disintegration or violent disintegration, the Big Crunch imagines a narrowing of space-time caused by gravity. The idea behind this situation comes from the thought that the expansion of the universe could finally slow down, stop, and turn around if the pull of all the matter in the universe was strong enough to counteract the pull of dark energy. In the early days of studying the universe, many scientists thought that gravity might win out over the growing universe's speed. The universe is expanding according to this idea, and matter is spreading out more. However, the universe's gravitational pull could finally slow down and then stop the growth. As contraction starts, galaxies, stars, and other objects in space will start to move closer together. Over very long periods of time, this process would end in a dramatic collapse in which the universe is squished into a state similar to the Big Bang, in which it was very hot and dense. The dynamics of the Big Crunch are governed by the interplay between the total mass energy of the universe and the expansion rate. In classical cosmology, the fate of the universe is determined by its density relative to a critical density. If the actual density exceeds this critical threshold, gravitational forces are strong enough to eventually stop and reverse the expansion, leading to a Big Crunch. However, modern observations indicate that the universe is expanding at an accelerating rate due to dark energy, making the Big Crunch scenario seem less likely under current conditions. Yet the possibility remains intriguing within certain theoretical frameworks, particularly if dark energy were to evolve in such a way that its repulsive effect diminishes over time. During a Big Crunch, the universe gets smaller, which makes the temperature and mass of matter rise very quickly. As the space between the stars gets denser, stars would die and then come back to life, and galaxies would join and crash into each other in a final chaotic merging. Distances would eventually get so small that the universe would get close to a state where the laws of physics as we know them would no longer apply. This reversal of the expansion of the universe not only makes us wonder about the end of the universe, but it also suggests that there might be a new beginning. In this cyclical process, the collapse could set off conditions like those during the Big Bang, which could lead to another phase of expansion. There are mathematical versions of the Big Crunch that come from the Friedmann equations of general relativity. These equations show how the universe's growth changes over time. If the density parameter omega pi is bigger than 1, these formulae show that the universe is closed and there will be a Big Crunch. However, studies of cosmic microwave background radiation and large-scale structure show that omega is very close to 1, and dark energy makes up most of the universe's energy balance. However, different theories of gravity or changes to the properties of dark energy might make it possible for a Big Crunch to happen, even though present data point to the universe expanding forever. The possibility of universal rebirth is one of the most important effects of the Big Crunch scenario. Some cyclic models say that the universe's fall might not be the end of everything, but rather the start of a new Big Bang, which would restart the clock on evolution. In these models, the universe goes through an infinite number of rounds of growing and shrinking, with each cycle wiping out the records of the one before it. This circular view isn't what most cosmologists agree on, but it does offer a fascinating story in which the universe is seen as something that is always changing and growing, instead of something that has a single, final end. Despite its theoretical allure, the Big Crunch faces significant challenges in light of observational data. The accelerating expansion of the universe, driven by dark energy, is currently the dominant trend, making the conditions required for a reversal of expansion appear unlikely. Yet the Big Crunch remains a valuable concept for exploring the limits of gravitational theory and understanding how the interplay of mass, energy, and space-time curvature could, under different conditions, lead to a radically different cosmic outcome. Cyclic or bouncing universes, repeated cosmic rebirths. Cyclic or bounce universe models show how the universe has changed over time in a very different way than situations that promise a single, final, and unchangeable end. According to these models, the world goes through endless rounds of expanding and contracting. This means that what we think of as an end is actually just a stage on the way to a new beginning. The universe doesn't end in a final heat death, big rip, or big crunch. Instead, it goes through a number of bounces, with each cycle wiping out the leftovers of the last and possibly causing conditions similar to those of the Big Bang. The oscillatory universe is one of the first cycle models. It was put forward as an option to a single event that created the universe. In this picture, the universe starts out very small, grows until it's at its biggest, and then it shrinks because of gravity, finally falling back to a very small size. Instead of being the end, this collapse is thought to start another growth, a bounce, that restarts the cosmic clock. The idea comes from the thought that the rules of physics, especially those that drive gravity and thermodynamics, might let expansion stop when certain conditions are met. Modern cyclic models have evolved significantly from these early ideas. For instance, the ekperiodic and cyclic models proposed by Paul Steinhardt and Neil Turok introduced the concept of brane cosmology, where our observable universe is a three-dimensional brane embedded in a higher dimensional space. In this framework, collisions between branes could trigger periodic Big Bangs, leading to a new cycle of expansion. These models aim to address some of the shortcomings of the traditional Big Bang theory, such as the horizon and flatness problems, while providing a mechanism for cyclic renewal. They also offer an elegant way to conceptualize entropy. Rather than accumulating endlessly, entropy is somehow reset or diluted during each bounce, preserving the possibility of structure and complexity in successive cycles. The perceived constant rise in entropy, which is required by the second law of thermodynamics, is one of the biggest problems that cyclic models have to deal with. In a simple closed system, entropy should keep going up until it reaches a state with the most chaos. However, cyclic models suggest that mechanisms exist to counteract or reset entropy at the end of each cycle. Some ideas say that during the contraction phase, things like black hole evaporation or quantum gravity effects might reset the entropy, making way for a new phase with less entropy. Even though these ideas are still just guesses and are being talked about, they do open up some interesting possibilities for keeping the world constantly changing. Different statements can be made by cyclic models, which can be checked with tools from now and in the future. For instance, the patterns left behind by the cosmic microwave background, CMB, could have signs of past cycles, like certain oddities or structures that appear over and over again. Large-scale features in the universe, such as galaxy groups and cosmic voids, may also show us how they were spread out during past contractions and bounces. Observations so far mostly point to dark energy speeding up the expansion, but periodic events are still possible if certain conditions are met or the standard model of astronomy is changed. The implications of cyclic universes extend beyond mere cosmic mechanics. They challenge our fundamental notions of time and causality. In a cyclic model, the universe does not have a definitive beginning or end. Instead, time becomes an infinite loop of creation and destruction. This view not only offers a potential solution to the question of cosmic origin, but also frames our understanding of the future as an ongoing process, where each end is simply a prelude to a new beginning. There are some nice things about circular models, but they have a lot of problems with theory and data. Finding a reasonable way to restart entropy and explaining cyclic behaviour in a world that is expanding faster than ever is still one of the biggest problems. Furthermore, the more complex theories that these models are based on need additions to what we know about physics now. These include string theory and quantum gravity, which are still being worked on. Gamma-ray bursts, cosmic death rays from explosive events. GRBs, or gamma-ray bursts, are some of the most mysterious and intense cosmic occurrences ever seen. Cataclysmic cosmic explosions that happen billions of light years distant are believed to be the source of these powerful gamma radiation bursts, which can endure anywhere from milliseconds to several minutes. Though they don't last long, GRBs unleash more energy in a matter of seconds than the Sun will emit in its entire 10 billion year lifespan. Scientists view GRBs as important actors in cosmic development and, in certain cases, as triggers for the collapse of cosmic structures, because to their tremendous energy production and the huge areas of space they have the ability to impact. The origin of gamma-ray bursts is linked primarily to two distinct types of astrophysical phenomena. The first involves the collapse of massive stars, a process that can lead to a supernova or, in the most extreme cases, the formation of a black hole. In these so-called long-duration GRBs, the core of a massive star collapses under its own gravity, producing a hypernova, an extremely energetic supernova. During this collapse, powerful jets of material are expelled at nearly the speed of light, and if one of these jets is pointed directly toward Earth, we observe a gamma-ray burst. The second type, associated with short-duration GRBs, is believed to arise from the merger of compact objects, such as neutron stars, or a neutron star with a black hole. These violent collisions also generate intense bursts of gamma rays, though they typically last less than 2 seconds. Space observatories like the Fermy and Swift satellites, operated by the National Aeronautics and Space Administration, are able to detect gamma-ray bursts through observation. In order to detect GRBs, which are characterized by abrupt, powerful flashes, these devices scan the sky around the clock. Astronomers are able to examine burst afterglows over a variety of wavelengths, from radio waves to X-rays, thanks to the data relayed by these satellites to ground-based observatories. The burst surroundings and distance may be better understood, along with the explosion's driving forces, by studying the afterglow. The possible effect of GRBs on the cosmos is among its most important features. The great energy emitted during these occurrences makes gamma-ray bursts capable of influencing vast areas. A GRB in a neighbouring galaxy, for instance, can perhaps destroy a planet's protective ozone layer, therefore exposing its surface to dangerous UV radiation and leading to mass extinctions. On a cosmic level, regular GRBs in the early universe might have helped to control star creation by energizing the nearby interstellar medium, hence affecting the history of galaxies. The physics behind gamma-ray bursts involves several complex processes. In the case of long-duration GRBs, the collapse of a massive star leads to the formation of a black hole or a rapidly spinning neutron star known as a magnetar. The tremendous gravitational forces involved, combined with the magnetic fields of these compact objects, drive the formation of highly collimated jets that pierce through the star's outer layers. As these jets escape into space, internal shocks within the jets, caused by variations in the velocity of the expelled material, accelerate particles to near-light speeds. These particles then interact with magnetic fields, emitting gamma rays in the process. The rapid variability and high energies observed in GRBs can be explained by this internal shock model, though alternative models, such as magnetic reconnection, are also being explored. For short-duration GRBs, the merger of neutron stars is a leading explanation. When two neutron stars spiral together and collide, they produce an extremely energetic explosion that can launch jets similar to those seen in long-duration GRBs. In addition to gamma rays, these events are also associated with the production of heavy elements through a process known as R-process nucleosynthesis, which occurs in the extremely neutron-rich environment created during the merger. The detection of gravitational waves from such mergers by observatories like LIGO and Virgo has provided additional evidence supporting the neutron star merger model for short GRBs. Understanding cosmic development and the ultimate fate of the universe depends much on the research of gamma-ray bursts. In situations when GRBs arise often in specific places, their strong energy release might act as a sterilizing agent over large swaths of space, hence perhaps impeding the emergence of life. Furthermore, the energy injected by GRBs into the intergalactic medium might change the temperature history of the cosmos, therefore impacting the formation and evolution of galaxies over billions of years. Moreover, GRBs offer a natural setting for experimenting on the boundaries of high-energy physics. Extreme circumstances seen in a gamma-ray burst, such as ultra-relativistic speeds, strong magnetic fields, and fast particle acceleration, offer insights into physics processes challenging to replicate on Earth. From particle acceleration processes to the behavior of matter under severe circumstances, this then helps improve theoretical models and shapes our knowledge of fundamental physics. Asteroid impacts, the ever-present cosmic threat. Long acknowledged as a regular and serious threat to life on Earth, and thus to the evolution of cosmic structures, are asteroid strikes. Unlike the more exotic and far future ideas of cosmic ends, asteroid strikes are a real threat that has moulded the history of our planet and still causes problems now. Reviewing past occurrences that have had significant consequences on Earth, this segment looks at the science underlying asteroid impacts and addresses present efforts and future plans for identifying and reducing these cosmic hazards. Early in the development of our solar system, asteroid collisions were common and vital for the formation and evolution of planets. Countless asteroids and comets crashed into the early Earth during the turbulent era known as the Late Heavy Bombardment, shaping its surface and bringing water and organic chemicals that could have been necessary for the beginning of life. Although many of these effects were disastrous on a planetary level, they also helped to enrich the crust of Earth chemically, therefore enabling later geological and biological development. About 66 million years ago, the Chicxulub event, one of the most well-known and catastrophic asteroid strikes, occurs. A roughly 10-kilometre wide asteroid is thought to have had this effect, which set off the mass extinction event, wiping off the non-avian dinosaurs along with many other species. Equivalent to billions of atomic bombs, the Chicxulub impact generated shockwaves, huge tsunamis, and a global environmental disaster. The dust and aerosols thrown into the sky greatly lowered sunlight, therefore upsetting photosynthesis and causing extensive ecological collapse. This historical event models the devastating force of such crashes and reminds us sharply of the possibility for asteroid impacts to create fast, major changes on Earth. Modern astronomical surveys have revealed that Earth-crossing asteroids are not mere relics of the past. They continue to orbit the Sun, with some posing a potential threat to our planet. Dedicated programs such as NASA's Near-Earth Object Observations (NEOO) program and projects like the NEOWISE mission are actively scanning the skies to detect and track these objects. Advanced telescopes and radar systems have improved our ability to catalogue near-Earth objects, NEOs, enabling scientists to estimate their size, composition, and orbital trajectories. This growing body of observational data is critical for assessing the risk of future impacts and for developing strategies to prevent or mitigate them. The idea of asteroid deflection is one interesting way to help to prevent impacts. Many methods have been suggested to change the course of an asteroid, therefore lowering the possibility of a collision with Earth. One approach uses a kinetic impactor, a spaceship meant to collide with an asteroid at great speed, therefore imparting momentum and pushing it off course. For instance, NASA's DART, Double Asteroid Redirection Test, project seeks to test this idea by purposefully colliding with the moon of an asteroid to track the subsequent orbital adjustment. The gravity tractor approach is another option, whereby a spaceship positioned close to the asteroid gradually changes its trajectory over time by use of the gravitational attraction. Though such approaches come with great dangers and uncertainties, more dramatic options involve the deployment of nuclear explosions, either to vaporize a chunk of the asteroid or to impart a major momentum change. Asteroid impacts also have broader implications for our understanding of planetary defense. The potential devastation caused by a large asteroid has spurred international cooperation in monitoring and preparing for such events. Organizations such as the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG, work collaboratively to share data, coordinate observations, and develop contingency plans. These efforts not only improve our ability to detect hazardous objects, but also foster a global response framework that could one day prevent a catastrophic impact. Scientifically, research into asteroid collisions offers important new angles for understanding the dynamics of our solar system. Asteroids' compositions and paths expose details on the circumstances that dominated early planet formation. Records of prior collisions, impact craters on Earth and other celestial bodies provide hints on the frequency and size of these occurrences across geological time. This information then enables models of planetary formation, solar system mass distribution, and long-term development of celestial orbits to be refined. While the probability of a catastrophic asteroid impact in the near future is low, the potential consequences are so severe that even a low probability event warrants serious attention. The ongoing development of detection technologies and impact mitigation strategies is a testament to humanity's commitment to safeguarding our planet. As our observational capabilities continue to improve and our understanding of asteroid dynamics deepens, we move closer to a future where the threat of asteroid impacts can be effectively managed. Supernovae and stellar deaths. The life cycle of stars. Among the most amazing and powerful phenomena in the cosmos are supernovae and star deaths. Along with marking the spectacular end of a star's existence, they are vital for the development of galaxies and the chemical enrichment of the cosmos. We investigate the several kinds of supernovae, the mechanisms under control of star death, and their broad consequences for cosmic development in this subsection. Stars, like living organisms, have life cycles governed by their mass and composition. For most stars, the journey begins with the fusion of hydrogen into helium in their cores, a process that releases tremendous energy and supports the star against gravitational collapse. However, as a star exhausts its hydrogen fuel, its core begins to contract under the force of gravity, leading to changes in its internal structure. For stars with masses similar to or less than our Sun, this evolution culminates in the formation of a white dwarf, a dense remnant that cools over billions of years. In contrast, more massive stars undergo a more violent end. In massive stars, those at least 8 times the mass of the Sun, the exhaustion of nuclear fuel leads to a catastrophic collapse. As the core contracts, temperatures and pressures soar, enabling the fusion of heavier elements in successive stages. This process continues until iron is produced. Unlike lighter elements, fusing iron does not release energy. In fact, it consumes energy, leaving the star unable to support itself against its own gravity. When the iron core reaches a critical mass, it can no longer withstand the gravitational pressure and collapses almost instantaneously. This collapse is followed by a rebound shockwave that propagates outward, triggering a supernova explosion, a brilliant, short-lived burst of light that can outshine an entire galaxy. There are two primary types of supernovae associated with stellar death. Type 2 supernovae occur in massive stars that still contain a significant amount of hydrogen in their outer layers. These explosions are characterized by the presence of hydrogen lines in their spectra. The core collapse of these stars leads to the formation of a neutron star or a black hole, and the outward explosion disperses elements synthesized during the star's life into the surrounding interstellar medium. This dispersal is crucial as it seeds the cosmos with heavy elements like carbon, oxygen, and iron, elements that are fundamental to the formation of planets and, ultimately, life. Conversely, Type Ia supernovae arise in binary star systems in which a white dwarf gathers mass from a partner star. The white dwarf experiences a runaway thermonuclear explosion when its mass surpasses the Chandra's output limit, about 1.4 times the mass of the Sun. Type Ia supernovae are important as standard candles for gauging cosmic distances and the universe's expansion rate, as their brightness is very homogeneous, unlike that of core collapse supernovae. The impact of supernovae extends far beyond their immediate surroundings. The shock waves produced by these explosions compress nearby gas clouds, potentially triggering new rounds of star formation, a process known as triggered star formation. This recycling of material is fundamental to the evolution of galaxies, as it continuously renews the interstellar medium and drives the chemical evolution of the cosmos. The heavy elements forged in the hearts of massive stars are essential for the formation of rocky planets and the complex chemistry required for life. In this way, supernovae serve as both the end of a star's life and the beginning of new cosmic cycles. Supernovae are, statistically, among the most often seen events in astronomy. Both ground-based and space-borne modern telescopes frequently vividly record these tremendous outbursts. Supernovae's light curves, the way their brightness varies with time, offer vital details about the explosion dynamics, the makeup of the progenitor star, and the energy emitted during the event. Furthermore, providing labs for research on high-energy astrophysics and the behavior of matter under severe circumstances are the remains of supernova explosions as the Crab Nebula. Supervolcanoes, Yellowstone, and other potential global eruptions. Supervolcanoes are some of the strongest natural forces on Earth. They can change the temperature and shape of the whole planet's surface. Supervolcanoes can spew out a huge amount of lava and volcanic ash all at once, while regular volcanoes only affect a small area when they explode. The Yellowstone caldera in the United States is one of the best-known examples. It is a huge system of volcanoes that has had many destructive events in the past. This part talks about the science behind supervolcanoes, how they might affect the whole world, and what is being done right now to keep an eye on them and lower the risks they offer. The term supervolcano refers to a volcanic center that has produced an eruption with a volcanic explosivity index of 8, the highest rating on the scale. Such eruptions can eject thousands of cubic kilometers of material, dwarfing the output of typical volcanic events. For example, the Yellowstone supervolcano is estimated to have produced eruptions that spewed vast amounts of ash and gases into the atmosphere, with effects that would have lasted for years or even decades. The resulting climate disruption could lead to significant cooling, widespread crop failures, and a cascade of ecological consequences. This phenomenon, often described as a volcanic winter, would severely impact human societies and natural ecosystems. A supervolcano explosion works by slowly building up magma in a big, shallow reservoir below the surface of the Earth. Over time, the pressure builds up until it's higher than the rock above it, which causes a huge amount of energy to be released. Geological records show that Yellowstone's environment has been dramatically changed by past earthquakes, which may have also had an effect on the weather around the world. Scientists look at volcanic deposits, ash layers and environmental data to get an idea of how big, how often and what might cause supervolcano explosions. Monitoring supervolcanoes involves a multidisciplinary approach, combining seismic activity, ground deformation, gas emissions, and temperature changes. At Yellowstone, a network of seismographs, GPS stations and satellite observations continuously tracks the subtle movements and changes in the volcanic system. These measurements help scientists detect signs of increased activity that might precede an eruption. Although current data do not indicate an imminent eruption at Yellowstone, the possibility remains a subject of intense study and preparation. Besides Yellowstone, there are other supervolcanoes around the world that could be dangerous. These include those in New Zealand's Taupo volcanic zone and Italy's Campi Flegrei. The geology of each of these systems is different, and each has its own set of features. However, they can all explode in ways that have effects all over the world. Most of the work being done to reduce the danger of supervolcano events is focused on finding them early and being ready. It is not possible to stop a supervolcanic eruption from happening right now, but better tracking methods and emergency reaction plans can help lessen the effects on people. Researchers are also looking into models that can better predict how these systems will act. The goal is to make more accurate predictions about how likely eruptions are and what effects they might have. Pole reversal, Earth's magnetic field and its protective role. The Earth's magnetic field protects us from dangerous radiation from the Sun and space, but it is not steady. Over geological ages, its polarity can and does change. In this part, we look at geomagnetic reversals, find out how these changes might weaken Earth's protective shield, and talk about what that might mean for the environment and technology on our planet. The magnetic field is generated by the motion of molten iron and other metals in Earth's outer core, creating a geodynamo that produces a dipole field roughly aligned with the planet's rotational axis. This magnetic field extends far into space, forming the magnetosphere, which deflects charged particles from the solar wind and cosmic rays that could otherwise strip away the atmosphere or damage biological systems. However, geological records reveal that Earth's magnetic poles have reversed many times over the past 160 million years, with the most recent reversal occurring about 780,000 years ago. These reversals are not instantaneous, but occur over thousands of years, during which the field strength can drop significantly. A decrease in magnetic field strength during a pole reversal can lead to several potential hazards. A weakened magnetosphere may allow more solar and cosmic radiation to reach Earth's surface, potentially increasing the incidence of radiation-related health issues in living organisms and disrupting critical technological systems such as satellites, power grids, and communication networks. Moreover, higher levels of radiation could also impact the chemistry of Earth's atmosphere, potentially altering climate patterns over extended periods. Even with these risks, it's important to remember that geomagnetic reversals are natural events that have happened many times in Earth's past without destroying large parts of the animal kingdom. But today's world depends on technology a lot more than ecosystems did in the past. This makes us more exposed to the effects of a weaker magnetic field. For example, when there is a long time of weaker magnetic fields, more sun activity could cause geomagnetic storms. Power lines and pipes could get currents during these storms, which could damage infrastructure and cause widespread power blackouts. The famous Carrington event of 1859, a huge solar storm, shows how geomagnetic changes can make it hard for people to do things, even before computers. Monitoring the Earth's magnetic field all the time is very important to lower these risks. Scientists use a system of ground-based sensors and satellites to keep an eye on changes in the size and structure of the field. Their goal is to make better models that can predict how the geomagnetic field will behave. Better computer models and a better knowledge of how geodynamos work are helping us make more accurate predictions about future reversals and the effects they might have. Climate tipping points, natural limits, and abrupt changes. Climate tipping points are important levels in the Earth's climate system, above which even small changes can cause fast and often permanent changes. These tipping points aren't slow changes. Instead, they're rapid changes that can completely change the world on a global scale. In this part, we look at the science behind climate tipping points, some of the most important limits that experts have found, and what might happen if these limits are crossed. Melting Arctic sea ice is one of the most well-known examples of a point where the climate changes quickly. The Earth's albedo, or its ability to bounce sunshine back into space, goes down as world temperatures rise. Since there is less ice to reflect sun energy, the oceans take in more heat, which speeds up warming in a loop that feeds on itself. If a certain point is reached, this process might not be able to be stopped in the time it takes for humans to live. This could cause huge changes in the Arctic's weather patterns, water currents, and even ecosystems. The melting of permafrost in the Arctic areas is another important tipping point. Permafrost has a lot of frozen biological matter that breaks down into warming gases like carbon dioxide and methane when it thaws. These gases strongly contribute to global warming and could start a chain reaction of more warmth and soil melting, which would greatly speed up climate change. Especially the release of methane is a reason for worry, because over short periods of time, it has a much higher potential to warm the planet than carbon dioxide. The collapse of major ice sheets, such as those in Greenland and Antarctica, represents yet another potential tipping point. The disintegration of these ice sheets could lead to rapid sea level rise, threatening coastal communities and ecosystems worldwide. The dynamics of ice sheet collapse are complex, involving interactions between atmospheric warming, ocean currents, and the internal mechanics of ice flow. Once initiated, the process might reach a point of no return, where the ice sheet disintegrates even if global temperatures were to stabilize or decrease. Changes in ocean circulation patterns, such as the weakening of the Atlantic Meridional Overturning Circulation, AMOC, which is essential for controlling temperature across Europe and North America, also might be tipping points. A major slowdown or collapse of the AMOC might cause sudden regional cooling and a variety of related climate disturbances. Knowing these tipping points is essential, as they mark the limits beyond which slow changes might unexpectedly turn fast and permanent. Observational data and scientific models point to several of these thresholds, perhaps being closer than previously believed, which emphasizes the need of reducing greenhouse gas emissions and thereby stabilizing the world temperature. Although specific timing of these tipping points is yet unknown, the possibility of sudden climatic changes emphasizes the need of strong monitoring and flexible solutions to control the hazards. Solar storms, modern vulnerabilities to extreme space weather. Driven by strong sun eruptions, solar storms seriously endanger contemporary infrastructure and technologies. Usually connected with solar flares and coronal mass ejections, CMEs. These strong occurrences arise when the sun generates a burst of charged particles and electromagnetic radiation. Once these strong emissions reach Earth, they can set off geomagnetic storms that disturb satellite operations, networks of communication, and power systems. The Carrington event of 1859 is among the most spectacular historical records of a solar storm. Widespread auroras seen at low latitudes and disturbance of telegraph networks worldwide were brought on by this large solar flare and consequent CME. Although at the time technology was somewhat basic, the occurrence underlined the possibility of solar storms generating major, broad disturbances. A comparable or even modestly large solar storm might have disastrous effects in today's increasingly technologically dependent, and linked civilization. For example, induced currents from geomagnetic disturbances can compromise modern power networks and cause transformer failures and prolonged blackouts. Scientists are actively working to improve our forecasting and understanding of solar activity. Space-based observatories like the Solar Dynamics Observatory, SDO, and the Advanced Composition Explorer, ACE, monitor the Sun continuously, providing real-time data on solar flares, CMEs, and the solar wind. These observations enable more accurate predictions of when and how solar storms will impact Earth. Additionally, computer models and simulations are being developed to better understand the interactions between solar emissions and Earth's magnetosphere, which is critical for designing more resilient infrastructure. Strategies for mitigating also take front stage. Minimizing the effect of solar storms depends on developments in satellite shielding, grid management, and emergency response systems. We can lower the danger these extreme space weather events provide by strengthening the resilience of important systems and creating fast response policies. Black hole time dilation: how gravity alters time's flow. Einstein's theory of general relativity makes one of the most surreal predictions. Time itself is not constant, but rather influenced by mass and energy. Time dilation is a phenomena that is increasingly noticeable close to very big objects like black holes. Time slows down relative to locations with lesser gravity in regions of strong gravitational pull, a theory that questions our daily understanding of time as a consistent, unchangeable background. The fundamental concept of gravitational time dilation is that the rate that time passes depends on the curvature of spacetime generated by a large object. For a non-rotating, spherically symmetric mass, the Schwarzschild solution to Einstein's field equations offers a mathematical statement of this effect. The Schwarzschild metric states that time passes slower for an observer nearer a huge entity than for an observer farther away. Practically speaking, the clock on your spaceship would run far more slowly than the clock of a distant observer if you were hovering close to the event horizon of a black hole, a barrier beyond which nothing could escape. For example, imagine an astronaut venturing close to a black hole and then returning to Earth. Due to the strong gravitational field near the black hole, the astronaut's clock would run significantly slower compared to clocks on Earth. What might seem like a few hours for the astronaut could equate to many years passing on Earth. This isn't merely a theoretical curiosity. Time dilation has been experimentally confirmed in less extreme conditions. Even at the speeds achieved by satellites orbiting Earth, differences in time are measurable, a phenomenon that must be corrected for in the Global Positioning System, GPS, to ensure accurate positioning. Time dilation reaches remarkable degrees in the harsh environment close to a black hole. From the standpoint of an external observer, time seems to almost stop as an object approaches the event horizon and the gravitational attraction strengthens. Our knowledge of cosmic occurrences depends much on this influence. If a star were to go too near a black hole, for example, the time dilation experienced would cause the black hole's final consuming to seem to take an inordinately long period, even from the star's own point of view. Gravitational time dilation isn't just confined to black holes. Any massive object can cause time to slow down in its vicinity, though the effect is most dramatic near extremely dense bodies. This has important consequences for high-precision experiments and our understanding of the universe's structure. In regions where massive clusters of galaxies exert significant gravitational forces, subtle differences in the passage of time can affect the measurements of cosmic distances and the dynamics of galaxy clusters. Such effects are crucial for interpreting observations in cosmology, where precise time measurements help us trace the history and expansion of the universe. Furthermore, feeding into our knowledge of the ultimate fate of the universe is the interaction between time dilation and cosmic evolution. Mass distribution, and so gravitational effect in different areas will change as the universe grows and dark energy speeds this expansion. Time will pass more slowly in areas dominated by huge objects like black holes relative to less crowded environments. This asymmetrical flow of time may affect our models of the long-term development of the universe and even the ultimate end scenarios, such as the heat death or Big Rip. The idea that black holes can slow down time also opens up interesting new areas to study in the future. For example, studying the exact effects of gravity on time could help us make better models of how black holes behave, which could lead to big steps forward in our understanding of quantum gravity. Watching the light, curves from black holes merging or gravitational wave signals from black holes accreting are also advanced observational methods that can be used to measure time dilation effects and test the predictions of general relativity in very harsh circumstances. Black hole evaporation, Hawking radiation and long-term cosmic evolution. A deep theoretical idea, black hole evaporation connects quantum physics with general relativity. Stephen Hawking first proposed in the 1970s that black holes are not totally black, but rather gradually lose mass over time via a mechanism called Hawking radiation. Quantum events close to the event horizon produce this radiation from particle-antiparticle pairs formed from the vacuum. Every now and again, one of these particles drops into the black hole, while the other escapes, causing the black hole to gradually lose mass. The mechanism behind Hawking radiation involves the inherent fluctuations in the quantum vacuum. In the vicinity of the event horizon, the strong gravitational field can separate virtual particle pairs before they annihilate each other. The particle that escapes becomes real, carrying away energy in the form of radiation, while the other, with negative energy relative to an outside observer, is absorbed by the black hole. Over vast timescales, this process causes the black hole to slowly evaporate. The rate of evaporation depends on the black hole's mass. Smaller black holes emit radiation more rapidly than their larger counterparts, meaning that micro-black holes could evaporate relatively quickly, whereas supermassive black holes would take far longer to dissipate. The concept of black hole evaporation has significant implications for the long-term evolution of the universe. As black holes lose mass and eventually vanish, they release energy back into the cosmos, contributing to the overall thermal evolution of the universe. In an extremely distant future, over incomprehensibly vast timescales, Hawking radiation could play a pivotal role in driving the universe toward maximum entropy, ultimately leading to heat death. In this state, the universe would be characterized by a nearly uniform distribution of energy, with all gravitationally bound structures having long since dissipated. Black hole evaporation begs interesting issues concerning the preservation of information, a dilemma sometimes referred to as the black hole information paradox. What happens to the knowledge about the substance that sank into black holes if they finally vanish totally? This paradox has prompted a lot of study, resulting in ideas using quantum gravity theories and holographic ideas meant to solve these problems. Considered as one of the main difficulties in contemporary theoretical physics, the resolution of this dilemma has possible consequences for our knowledge of the basic character of space-time. For black holes with a star mass or more, the Hawking radiation impact is so small that observational proof of its existence is still difficult. Still, developments in quantum gravity and high-energy astrophysics are enhancing our theoretical models over time. To determine whether Hawking's predictions are correct, we may need to wait for future observations of miniature black holes as they evaporate or do analog experiments in a controlled environment. Time crystals, new states of matter that challenge. Time's arrow. A new idea in physics that questions our accepted knowledge of time and equilibrium are time crystals. Time crystals show periodicity in time unlike conventional crystals, which show a periodic pattern in space. This implies that they move continuously, oscillatively, even in their lowest energy state, therefore violating time translation symmetry. Originally suggested theoretically, the idea has been accomplished experimentally in under-control quantum systems. The discovery of time crystals suggests that there can be states of matter that never reach traditional equilibrium, continuously cycling through a series of configurations. This perpetual motion without energy input is counterintuitive because it appears to defy the conventional wisdom of thermodynamics, which posits that systems should eventually settle into a static equilibrium state. Instead, time crystals maintain a dynamic structure, raising fundamental questions about how we define the passage of time at the microscopic level. In the context of cosmic evolution, time crystals offer a fascinating glimpse into how new states of matter might exist under extreme conditions. They serve as a proof of concept that the arrow of time, as dictated by entropy, is not an absolute property, but can be influenced by quantum mechanical effects. This has intriguing implications for the fate of the universe, particularly in scenarios where the traditional flow of time might be altered, such as near black holes or during phase transitions like vacuum decay. Usually involving systems of interacting spins or atoms trapped in optical lattices, experimental realization of time crystals has included external periodic driving forces leading to the formation of these non-equilibrium states. These investigations not only confirm the theoretical expectations, but also provide fresh directions for investigating quantum coherence and the behavior of matter under situations resembling the severe environments observed in astrophysical surroundings. Quantum immortality, survival in a multiverse of outcomes. Derived from the many worlds interpretation of quantum physics, quantum immortality is a notion implying that all conceivable results of a quantum event take place in branching worlds. In this perspective, an observer might never die, as in at least one branch they still survive, despite apparently lethal circumstances. Though the concept is sometimes discussed in science fiction, its roots are in sober debates on the essence of quantum measurement and probability. In the context of cosmic evolution, quantum immortality offers a speculative, yet scientifically grounded perspective on how life might persist across the vast multiverse. According to this view, even if catastrophic cosmic events, such as vacuum decay or the Big Freeze, are inevitable in some branches of the multiverse, there may always be a branch in which an observer continues to exist. This notion challenges our traditional understanding of mortality and the finality of death, raising questions about the continuity of consciousness in an ever-branching reality. Still, the idea of quantum immortality is still rather debatable and hypothetical. Although it results from the same mathematical framework supporting successful quantum theories, applying it to the survival of conscious observers challenges empirical testability. Most readings of quantum physics remain indifferent regarding the subjective experience of branching, and the theory of quantum immortality does not now generate testable predictions. The Higgs field, mass, symmetry breaking, and vacuum stability. Modern particle physics is built on the Higgs field, which also explains why particles have mass and how our world is kept in structure. Found indirectly by 2012 Large Hadron Collider observations of the Higgs boson, the Higgs field penetrates all of space. Though at lowest energy form, the Higgs field is believed to have a non-zero value everywhere, unlike other fields that could vanish in a vacuum. The breakdown of electroweak symmetry by this continuous, ubiquitous field differentiates the electromagnetic and weak nuclear forces, therefore providing mass for elementary particles. The mechanism of spontaneous symmetry breaking defines the core of the standard model of particle physics. Under some transformations, the rules controlling particles first show symmetry. But the Higgs field gains a non-zero vacuum expectation value, VEV, hence selecting a certain direction in the configuration space of the field. This decision disturbs the symmetry of the fundamental equations. Particles interacting with the Higgs field thus gain mass commensurate with the degree of their interaction with the field. For example, top quarks, particles that interact more strongly with the Higgs field, are much heavier than electrons, which pair more weakly. Mathematically, the potential energy associated with the Higgs field is often modelled by the Mexican hat, or wine bottle, potential. V of phi equals lambda times the square of the quantity, absolute phi squared minus v squared over 2. The minimum of this potential does not occur at zero, but rather at a non-zero value, determined by the field's self-coupling and vacuum expectation value, VEV. This non-zero value is critical. It means that even the vacuum, the state of lowest energy, is not empty, but filled with a constant Higgs field. Through interactions with this field, particles acquire mass via the Higgs mechanism, fundamentally shaping the structure of matter in the universe. The Higgs field has important effects on the stability of the cosmos, in addition to significantly more limited ramifications for mass creation. The stability of our vacuum, that is, the condition in which the Higgs field resides, is very critical. Should our existing vacuum be indeed stable, the cosmos will persist in its current shape always. Theoretically, however, our vacuum may be metastable, a false vacuum, that finally collapses to a lower energy state. Quantum tunneling would cause such a degradation and result in a catastrophic phase shift, changing the basic constants of existence. Recent calculations in quantum field theory, taking into account the masses of the Higgs boson and the top quark, indicate that we might be living in a metastable vacuum. Although the probability of vacuum decay is exceedingly small on human timescales, over billions or trillions of years, even a tiny decay rate could eventually lead to a phase transition. This possibility, while speculative, raises profound questions about the long-term fate of the universe and the role that fundamental particles play in cosmic evolution. The ideas of symmetry in nature are closely related with the Higgs field. Although its non-zero VEV disturbs the symmetry of the electroweak force, it also suggests deeper symmetries may be found at higher energy levels. Many ideas beyond the standard model, such as supersymmetry or many grand unified theories, predict the existence of extra fields and symmetries that might affect the behavior of the Higgs field. These theories seek to present a more coherent picture of the forces of nature and may give means to stabilize the vacuum, therefore averting a catastrophic phase shift. Experimental efforts to measure the properties of the Higgs boson with increasing precision are ongoing. These measurements not only test the predictions of the standard model, but also probe for signs of new physics that could impact vacuum stability. In parallel, advances in particle accelerators and observational cosmology are helping to refine our understanding of the universe's energy content, including dark energy and dark matter, which together with the Higgs field play a crucial role in determining the ultimate fate of the cosmos. Proton decay, the slow disintegration of matter. Many grand unified theories anticipate a theoretical process called proton decay, implying that even the most stable constituents of matter could not be everlasting. These simulations suggest that protons, once believed to be completely stable, may eventually decay into smaller subatomic particles over incredibly vast timescales. If this gradual disintegration of matter takes place, it will have significant consequences for the long-term history of the cosmos, as it will indicate that the atoms building all structures, from stars to planets, are finally ephemeral. The possibility of proton decay arises from attempts to unify the fundamental forces of nature under a single theoretical framework. In the standard model of particle physics, protons are stable due to the conservation of baryon number, a quantum number assigned to particles like protons and neutrons. However, many extensions of the standard model, such as certain grand unified theories, GUTS, and supersymmetric models, predict that baryon number conservation may only be an approximate symmetry. In these theories, protons can decay via processes mediated by heavy gauge bosons, or other exotic particles that exist at very high energy scales, far beyond the reach of current particle accelerators. The decay channels predicted for protons typically involve the transformation of a proton into a positron and neutral pions, among other possible combinations. For example, a common decay mode proposed is P goes to E++ pi 0. Here, a proton decays into a positron and a neutral pion, with the pion subsequently decaying into 2 gamma rays. The detection of such decay products in a controlled experimental setting would provide crucial evidence for new physics beyond the standard model. Over the past decades, large underground detectors such as Super Kamiokande in Japan have been searching for signs of proton decay, but no conclusive evidence has yet been observed, leading to ever-increasing lower bounds on the proton's lifetime. From the point of view of cosmology, proton decay has big effects on what will happen to the world in the end. If protons decay over astronomically long periods of time, all matter as we know it would slowly break down, leading to a world where radiation and basic particles rule. In situations like the heat death, this process would be very important. In this case, after all the big structures have broken down, even the building blocks of atoms would finally disappear. Loss of protons would not only mean that matter is breaking down, but it would also mean that the universe's makeup and behavior have changed fundamentally over very long periods of time. Particle physics experiments are also driven by the theoretical study of how protons decay. Scientists are trying to catch very rare decay events that could either prove or disprove the claims of different grand unified theories by pushing the limits of how sensitive detectors can be. For these tests to work, huge, very sensitive devices need to be buried deep underground to protect them from cosmic rays and other background noise. So far, no observations of proton decay have put strict limits on the parameters of many theoretical models. This helps scientists improve or rule out certain extensions of the standard model. Quantum tunneling and the stability of the universe. Our knowledge of the long-term stability of the cosmos depends much on quantum tunneling, a phenomena wherein particles pass past energy barriers judged impenetrable by conventional physics. Quantum tunneling could enable transitions between many vacuum states in cosmic settings, hence perhaps inducing a phase change in the fabric of the cosmos. Although somewhat unusual on human timescales, this process might eventually decide whether our universe stays in its present form or veers into a quite different one. Within the framework of quantum field theory, the vacuum is a dynamic state full of changing energy levels rather than being an empty space. These variations provide an energy scene including several local minima. Our cosmos is believed to be in a false vacuum condition, a metastable arrangement in which the energy exceeds the absolute minimum, or true vacuum. Because of quantum tunneling, the fake vacuum is intrinsically unstable, even if it can last billions of years. A bubble of actual emptiness might develop inside the illusory vacuum via a means of tunneling. Once nucleated, this bubble would spread at the speed of light, transforming the surrounding area into a new state with different physical characteristics. The probability of such a tunneling event is given by the expression gamma is approximately A times E to the power of negative B over h bar. Here, gamma represents the decay rate per unit volume. A is a prefactor determined by the specifics of the energy barrier. B corresponds to the action associated with the tunneling process, and h bar is the reduced Planck constant. The exponential suppression in this equation implies that, while the probability is non-zero, it is extremely small under typical conditions. However, given the vast volume of the universe and the unfathomable timescales involved, even an exceedingly small decay rate could eventually lead to a phase transition that would fundamentally alter the laws of physics. Such a change has enormous consequences. The shift in vacuum energy would entail a radical reorganization of the basic forces and particle masses should our universe tunnel into a genuine vacuum state. Practically speaking, This suggests that the constants controlling the interactions of matter may change, resulting in conditions unfriendly to the kinds of structure we already know. Galaxies, stars, even atoms might be made unstable. Even if a new vacuum state may thereafter develop with their own unique set of physical rules, such an event essentially marks the end of the universe as we know it. Quantum tunneling also offers insights into the broader question of cosmic stability. It challenges the notion that the current state of the universe is permanent by introducing a mechanism through which a catastrophic phase transition could occur. This possibility forces physicists to consider the fine balance between different vacuum states and to refine models of the universe's evolution that incorporate both classical gravitational dynamics and quantum mechanical effects. Current actual data does not show that a vacuum decay is about to happen, but the study of quantum tunneling in cosmology has big effects on how we think the universe will end. This theory gives us a way to think about how stable our vacuum state is over the long term and how long it might take for a shift to happen. High-energy physics and quantum gravity study are also looking into these questions to find out if the universe is really stable or just metastable, which is the most important question in cosmology. The James Webb Space Telescope, peering into cosmic origins. The James Webb Space Telescope, JWST, is the most advanced tool we have for studying the early universe and gives us new information about how the universe came to be. JWST was launched to look deeper into space and, by extension, further back in time. Its purpose is to see the first light of the universe, the birth of the first galaxies, and how cosmic structures change over billions of years. Astronomers can use its advanced set of equipment, which includes infrared images and spectroscopy, to find faint signs that have been travelling through space since the Big Bang. The most important thing that JWST can do is watch in the infrared range. When compared to visible light, infrared bands can pass through clouds of gas and dust that block many stellar objects. This is very important when looking at the early universe, when cosmic dust covers the galaxies that are just starting to form. By collecting infrared light, JWST can show details about how stars are formed and how galaxies are put together that were not visible before. This skill not only helps us learn more about the physical processes that are shaping the universe, but it also gives us important clues regarding the way the first galaxies and stars formed in the beginning of time. JWST is very good at taking pictures, and it also has strong spectroscopy tools that let us look closely at light from faraway objects. Scientists can figure out what galaxies and other astronomical things are made of, how hot they are, and how they move by breaking light into its individual bands. Redshifts tell us about the rate of cosmic expansion and the spread of matter in the early universe. Spectroscopy is needed to measure redshifts. By showing how dark matter and dark energy have affected the history of the universe, these data help improve theories of the universe. The huge segmented mirror of JWST is another amazing characteristic that offers an efficient collecting area significantly more than that of earlier space observatories as Hubble. JWST's higher light gathering capability pushes the envelope of our visible cosmos by enabling the detection of rather faint objects. JWST provides a direct insight into the early phases of the universe as it can record light that has been travelling for more than 13 billion years. Testing hypotheses regarding the primordial circumstances of the universe, including the nature of cosmic inflation and the mechanism behind the creation of major structures, depends on these findings. JWST's discoveries are expected to have profound implications for our understanding of cosmic origins and evolution. By mapping the distribution of the earliest galaxies and characterizing the physical conditions within them, JWST will help answer fundamental questions about how the universe transitioned from a nearly uniform state to one filled with the rich structure we observe today. Moreover, the telescope's observations will contribute to our understanding of the reionization epoch, a period when the first stars and galaxies ionized the neutral hydrogen that pervaded the early universe, fundamentally altering its transparency and setting the stage for subsequent cosmic evolution. The cosmic microwave background, echoes of the Big Bang. Acting as a fossil relic of the Big Bang, the cosmic microwave background, CMB, is among the most important sources of data on the early cosmos. Offering a glimpse of the universe when it was just 380,000 years old, a period when it had cooled enough for electrons and protons to mix into neutral hydrogen atoms, this weak glow of microwave radiation penetrates the cosmos. These atoms, known as recombination, signaled the moment the cosmos opened to radiation so photons could fly unhindered throughout space. These photons today create the CMB, a fairly homogeneous backdrop with faint temperature changes etched by primordial density differences. The significance of the CMB in cosmology cannot be overstated. Its discovery in 1965 by Arno Penzias and Robert Wilson provided robust evidence for the Big Bang theory, fundamentally shifting our understanding of the universe's origins. Detailed measurements of the CMB, particularly by satellites such as COBE, WMAP, and more recently, the Planck mission, have revealed tiny anisotropies, minute differences in temperature on the order of 1 part in 100,000. These fluctuations are not random. They represent the seeds of all current cosmic structures. Regions slightly denser than their surroundings eventually evolved into galaxies and clusters under the force of gravity. The study of the CMB offers understanding of many important cosmological factors. For example, the exact measurement of its temperature changes lets scientists ascertain the age, composition, and pace of expansion of the cosmos. Through analysis of the angular power spectrum of the CMB, one may deduce the density of dark matter, baryonic matter, dark energy, and even hints on the geometry of the universe. Current observations of a flat universe show that the total density of matter and energy is somewhat near to a critical number. This outcome has great consequences for the fate of the universe. The CMB provides a cosmic background against which the consequences of cosmic inflation, a fast expansion of the cosmos in its early years, may be observed. Specific patterns in the polarization and temperature variations of the CMB are predicted by inflationary models. Continuous measurements are verifying these predictions. The mark of inflation in the CMB not only supports our knowledge of the explosive origins of the cosmos, but also limits theoretical models aiming at uniting general relativity with quantum physics. Advanced techniques in data analysis, including machine learning algorithms, are now being applied to CMB datasets to extract even more subtle signals. These efforts are aimed at detecting phenomena such as primordial gravitational waves, which would leave a distinct signature in the CMB's polarization patterns. The detection of these waves would offer a direct glimpse into the physics of the early universe and further validate the inflationary paradigm. Dark energy and dark matter, unraveling the universe's mysteries. Together, making over 95% of the total energy density of the universe, dark energy and dark matter are two of the most mysterious elements of the cosmos. Though they are somewhat common, both remain enigmatic as they do not interact with light in the manner regular matter does. The observational data and theoretical difficulties related with these enigmatic events are investigated in this subsection together with how they affect our knowledge of cosmic development and the final fate of the universe. Dark matter, though invisible, reveals its presence through its gravitational effects. It plays a crucial role in the formation and stability of galaxies, as evidenced by the rotation curves of spiral galaxies and the gravitational lensing of light around massive galaxy clusters. These observations indicate that visible matter accounts for only a small fraction of a galaxy's total mass. Instead, a vast, unseen component, dark matter, provides a necessary gravitational pull to hold galaxies together. The leading candidates for dark matter include weakly interacting massive particles, WIMPs, and axions, yet despite decades of searches through direct detection experiments and collider studies, no definitive evidence has been found. This persistent mystery challenges physicists to refine existing models and develop innovative detection methods. Dark energy, on the other hand, is invoked to explain the accelerating expansion of the universe, a discovery that revolutionized cosmology in the late 20th century. Unlike dark matter, which exerts gravitational attraction, dark energy appears to have a repulsive effect, driving galaxies apart at an ever-increasing rate. Its properties are commonly described by the equation of state parameter WWW, which relates its pressure to its energy density. Observation suggests that W is near a critical value, consistent with a cosmological constant dot. However, if WWW were to deviate even slightly, it could have profound implications for the universe's fate, potentially leading to scenarios like the Big Rip, where the repulsive force eventually tears apart all cosmic structures. Not only is understanding dark energy and dark matter fundamental for describing present cosmic structure, but it also helps one forecast the long-term development of the cosmos. For instance, the equilibrium between dark energy and dark matter determines whether the universe will keep expanding endlessly, achieve a stable condition, or perhaps even collapse back in a big crunch. Moreover, the behavior of dark energy over time will directly influence the thermal and structural fate of the universe, so it is a fundamental component in any model projecting the end of the cosmos. The more we learn about observational cosmology, the more these puzzles are beginning to unravel. The characteristics of dark matter and dark energy are being constrained by high-precision observations made by spacecraft like the Planck satellite and by future missions aimed at studying supernovae and large-scale structures. Furthermore, detectors on Earth, such those at the Large Hadron Collider and at subterranean locations, are still looking for dark matter particles, and new observational techniques in gravitational lensing and cosmic vacuum mapping shed light on the role of dark energy. Particle accelerators and gravitational waves. Probing the extreme. Gravitational wave monitors and particle accelerators work together to help us understand the strangest things that happen in the world. On the one hand, particle accelerators like the Large Hadron Collider, LHC, recreate the early universe's high energy state. This lets scientists study the basic particles and forces that control how the universe evolves. By slamming particles together at almost the speed of light, the LHC helps us understand how matter acts in situations with very high energy levels. This helps us test ideas that go beyond the standard model. We learn more about things like symmetry breaking, the Higgs mechanism, and even possible signs of dark matter through these studies. On the other side, gravitational wave observatories like LIGO and Virgo have opened an entirely new window into the cosmos. Gravitational waves are ripples in space-time generated by some of the most violent events in the universe, such as the mergers of black holes and neutron stars. The detection of these waves has not only confirmed a major prediction of Einstein's general relativity, but also provided unprecedented data on the dynamics of massive cosmic collisions. These observations allow scientists to study how energy is distributed during such cataclysmic events and offer clues about the behavior of space-time under extreme conditions. These two fields, high-energy particle physics and gravitational wave astronomy, are very important for pushing the limits of our existing ideas. As an example, the LHC's tests help us figure out what might have happened during the Big Bang, and the discovery of gravitational waves shows us how black holes and neutron stars behave in real time. Both types of observations are necessary to study the very edges of classical physics, where quantum effects start to take over. This change could eventually affect how we think about the long-term future of the world. It is anticipated that a multi-messenger strategy would be encouraged by the increasing integration of data from particle accelerators and gravitational wave observatories, thanks to technological advancements. By considering the cosmos as a whole, we may better understand how the universe is structured and how quantum particles interact with one another and with spacetime as a whole. Quantum computing in cosmology, simulating existential risks. Quantum computing is becoming a revolutionary tool in the field of astronomy, allowing us to model complex quantum field interactions in curved spacetime in ways that have never been possible before. For example, this technology is great for simulating very rare cosmic events like vacuum decay or the dynamic processes that control dark energy, which are impossible to do with regular computer programs. Quantum computers use the ideas of superposition and entanglement to handle huge amounts of data and look into many quantum states at the same time. Researchers can now model the complex interactions between quantum fluctuations and gravitational effects. This is important for figuring out how the universe will change over time and what existential threats it might face. By utilizing quantum algorithms, scientists can create detailed models of cosmic phenomena that involve the delicate balance of energy and matter. For instance, simulations can help predict how subtle variations in vacuum energy might trigger transitions between different vacuum states, potentially leading to a catastrophic phase change. These quantum simulations also shed light on the behavior of dark energy, contributing to our understanding of its role in scenarios like the Big Rip. Additionally, the high computational power of quantum systems enables the exploration of parameter spaces that are too vast for classical computers, allowing for more robust testing of theoretical models. The insights gained from quantum computing in cosmology not only enhance our predictive capabilities regarding universe-ending scenarios, but also inform the design of future experiments. By identifying specific signatures or behaviors associated with extreme cosmic events, researchers can better target observational efforts, whether through gravitational wave detectors or next-generation telescopes. In this way, quantum computing is poised to bridge the gap between theoretical predictions and empirical data, offering a promising pathway toward unraveling some of the deepest mysteries of the cosmos. Rogue black holes, invisible wanderers of the galaxy. Rogue black holes, which are sometimes called invisible wanderers, are black holes that have been thrown out of their mother galaxies or formed on their own and are now floating through interstellar and even intergalactic space. Astronomers have a hard time finding these things because they are invisible. Since they don't give off light, rogue black holes can only be found indirectly by measuring how much matter they pull in. This part talks about how rogue black holes form, how they can be found, and the possible dangers they pose, as well as what they mean for our understanding of how the universe works in a more general way. The formation of rogue black holes can occur through several mechanisms. One pathway is the dynamic interactions within densely populated star clusters or galactic cores, where gravitational encounters between massive objects can sling a black hole out of its host system. Additionally, during the violent mergers of galaxies, gravitational interactions can eject one or more black holes into intergalactic space. These processes result in black holes that no longer reside in a stable orbit around a galaxy, but instead wander the cosmos. Since rogue black holes don't give off light, they are naturally hard to find. But we can figure out if they are there by looking at the gravity lensing effects they have. It is called gravitational microlensing when a rogue black hole moves between a faraway star and a person looking at it. This can bend the light from the star, making it temporarily brighter or distorted. By carefully watching these small changes in light, scientists can figure out that a black hole exists and get a rough idea of how fast and how much it weighs. Rogue black holes also have significant implications for the structure and evolution of galaxies. As these massive objects traverse through space, their gravitational fields can disrupt the orbits of stars and gas clouds, potentially triggering the formation of new stars or altering the dynamics of a galaxy's disk. In extreme cases, a rogue black hole passing close to a star system could perturb the orbits of planets, leading to collisions or ejections from the system. Such events, while rare, highlight the potential for rogue black holes to act as agents of cosmic change, influencing the evolution of the environments they traverse. Studying rogue black holes gives us useful information about how galaxies form and change over time. Their paths and interactions give us information about how gravity works in places where dark matter is common. They also help scientists improve models that show how galaxies form and interact over very long periods of time. Also, knowing how often and where rogue black holes appear could help us guess about other strange events, like the possibility that these objects could be the start of future galaxy mergers. Planet X or Nibiru, separating myth from scientific reality. People have been interested in the idea of a strange, unknown planet for decades, often called Planet X or Nibiru, thanks to scary claims and end-of-the-world predictions. Even though these ideas are common in pop culture, scientists are still not sure about them. They use strong observational evidence to tell the difference between myth and fact. This part talks about where the Planet X Nibiru theory came from, the astronomical proof for its presence, and the problems with modern observational methods that have led to these stubborn myths. Historically, the search for Planet X began with efforts to explain discrepancies in the orbits of known planets, particularly Neptune. Early astronomers posited that an unseen planet might be exerting gravitational influences on the outer solar system. While these early hypotheses eventually led to the discovery of Pluto, further studies revealed that Pluto's mass was too small to account for the observed anomalies. Over time, as telescopic technology advanced and our understanding of the solar system improved, the need for a massive undiscovered planet diminished. Modern versions of the Planet X concept endure, despite the scientific agreement, either driven by data misunderstanding or sensationalized media coverage. Though claims of a rogue planet on a collision course with Earth or one causing regular mass extinctions have gone around, reputable data does not support them. Actually, no object with the mass or size needed to endanger Earth has been found in thorough studies of the outer solar system, including those carried out by the Wide Field Infrared Survey Explorer, WISE, and other specialized missions. The persistence of the Nibiru myth highlights the challenges in communicating complex astronomical data to the public. In many cases, observed anomalies in the orbits of trans-Neptunian objects have been misinterpreted as evidence for an undiscovered planet, while some studies suggest the possible existence of a distant, massive planet influencing these orbits, a candidate often dubbed Planet 9. This is a far cry from the catastrophic Nibiru scenarios popular in pseudoscientific circles. Planet 9, if it exists, is hypothesized to be located in the far reaches of the solar system, with an orbit that would not bring it close to Earth. Alien invasion scenarios, cosmic explanations from the Fermi paradox. Though a mainstay of science fiction, alien invasion scenarios often show up in scientific debates as we work through the Fermi paradox, the seeming contradiction between the great likelihood of extraterrestrial life in the cosmos and the absence of data or interaction. This article looks at imaginative, scientifically grounded theories explaining why we have not yet seen alien civilizations and how these concepts can guide events involving extraterrestrial interaction or even possible dangers. The Fermi paradox can be explained in part by sophisticated civilizations deciding to remain hidden or to avoid interacting with less developed species, therefore adopting a non-interference policy. According to this zoo hypothesis, Earth may be purposefully isolated, just like animals in a nature reserve, which would leave us ignorant of a larger cosmic community. Alternatively, a situation frequently referred to as the Great Filter is that technological civilizations could self-destruct before they can create interplanetary communication. In this regard, the start of an extraterrestrial invasion may seem improbable only because very few civilizations endure long enough to go outside their own planets. Another scientific perspective considers that advanced civilizations may use technologies or communication methods that we are currently unable to detect. They might communicate through neutrinos, gravitational waves, or even through means that are completely unknown to us. As such, what we perceive as silence could actually be a form of communication in a spectrum beyond our current technological reach. This possibility opens up intriguing avenues for future research and suggests that the detection of extraterrestrial signals may require a paradigm shift in our observational techniques. There are also models proposing that alien civilizations could deliberately position themselves in strategic ways, such as at key cosmic nodes, which might explain anomalies in the distribution of matter or energy in our galaxy. While these ideas remain speculative, they provide a framework for understanding how contact with extraterrestrial life might eventually occur in a manner that is gradual and non-catastrophic, rather than as a sudden invasion. Advances in dark matter research, clues to the universe's fate. Our endeavour to know the ultimate fate of the cosmos depends much on developments in dark matter research. Dark matter clearly has gravitational effects, even though it does not produce, absorb, or reflect light, making it undetectable to conventional telescopic studies. Scientists are building a more complete picture of cosmic structure and development by mapping the distribution of dark matter and researching its interactions with visible matter, which in turn guides projections about the fate of the universe. Using gravitational lensing, where the gravitational field of dark matter bends and distorts the light from far-off galaxies, is one of the main methods scientists investigate dark matter. Detailed lensing maps show that dark matter creates a vast, complex framework on which galaxies and clusters build. These data not only support the existence of dark matter, but also assist to improve theories of its dispersion around the universe. Better understanding of this distribution is crucial, as dark matter drives the development of big-scale structures and affects the pace of universe expansion. Direct detection studies simultaneously challenge our knowledge of dark matter particles. Shielded from cosmic radiation, underground labs utilize very sensitive detectors to record the weak interactions between dark matter particles and atomic nuclei. These tests continue to place more strict constraints on dark matter's characteristics, therefore restricting the field of feasible theoretical possibilities, even if they have not yet offered conclusive proof of it. Complementary solutions to this difficult issue include particle accelerators such as the Large Hadron Collider, which are examining high-energy collisions for indications of dark matter generation. The role of dark matter is also intertwined with that of dark energy, which drives the accelerating expansion of the universe. Together, these components dominate the cosmic energy budget, and their interplay could dictate the universe's long-term behaviour. For instance, precise measurements of how dark matter clumps and evolves over time help constrain the models that predict whether the universe will expand forever, succumb to a big rip, or follow another fate entirely. To look ahead, new tests and telescopes are about to help us learn even more about dark matter. The gap between theory forecasts and observational data will be closed with the help of next-generation devices, more powerful particle accelerators, and better computer models. As we learn more about dark matter's qualities with these tools, they will give us important clues about how the universe works as a whole, helping us figure out what will happen in the end. Next-generation telescopes and observatories beyond JWST. The James Webb Space Telescope, JWST, has changed the way we think about the early universe, but we still have a long way to go before we can fully understand how the universe works. We hope that next-generation telescopes and sites will make our skills even greater, letting us look deeper into the universe with more accuracy and over a wider range of wavelengths. These high-tech tools are meant to build on what JWST has found, and also to answer new questions about dark matter, dark energy, and the fine structure of how the universe has evolved. Upcoming space-based observatories, such as the Nancy Grace Roman Space Telescope and potential successors to JWST, will offer enhanced infrared and optical sensitivity. These missions are expected to capture the faint light of the earliest galaxies, providing more detailed maps of the universe's infancy. Their advanced spectroscopic instruments will enable scientists to analyze the chemical composition and physical conditions of celestial objects with greater accuracy, refining our models of galaxy formation and evolution. A new breed of very big telescopes, like the Extremely Big Telescope, ELT, and the 30-meter telescope, TMT, will change the way we think about the universe on Earth. With their huge apertures and cutting-edge adaptive optic systems, these telescopes will be able to see small features in galaxies and star groups far away. This will help us understand where dark matter is located and how cosmic structures move. Their ability to take high-resolution pictures is especially useful for studying gravitational lensing effects, which can show small changes in space-time that could lead to new theories of physics. Future telescopes will be able to look at things in more than just the visible and infrared ranges. They will also be able to look at things in the radio and X-ray bands. Large telescopes like the Square Kilometre Array, SKR, and the Advanced Telescope for High-Energy Astrophysics, Athena, will work with optical and infrared telescopes to get a fuller picture of the universe. These findings at multiple wavelengths are very important for understanding things like how stars grow, how black holes gather matter, and how cosmic magnetic fields change over time. Gravitational wave astronomy, listening to the universe's cataclysms. Gravitational wave astronomy has given us a totally new way to look at the world. Gravitational wave monitors pick up ripples in space-time caused by some of the most violent events in the universe. This is different from regular cameras that pick up electromagnetic radiation. Catastrophic events like black holes merging, neutron stars colliding, and even supernova explosions send out these waves, which give us direct access to things we couldn't see before. Detectors such as LIGO and Virgo have already made groundbreaking observations, confirming key predictions of Einstein's general relativity and providing unprecedented details about the dynamics of compact objects. The detection of gravitational waves not only validates theoretical models, but also allows scientists to probe environments where extreme gravitational forces dominate, revealing the inner workings of events that generate these waves. For example, the detailed waveform data from merging black holes helps determine their masses, spins, and even the distance from Earth, thereby enriching our understanding of the population of these enigmatic objects. Gravitational wave science also has a bright future ahead of it. The planned Einstein telescope and the Laser Interferometer Space Antenna, LISA, are examples of next-generation telescopes that will make the range of frequencies that can be seen much wider and more sensitive. For example, LISA will be able to work in space and find lower frequency gravitational waves that devices on the ground can't see. This will help us understand supermassive black hole mergers and other big events in the universe. These devices will not only be able to pick up on more events, but they will also be able to show more subtle information about how the world is put together and how it has changed over time. Multi-messenger astronomy, the combination of gravitational wave data with electromagnetic observations, will help scientists cross-verify results and create a more whole picture of cosmic cataclysms. Scientists may test hypotheses about the ultimate fate of the universe and even modify models of how cosmic structures develop by aggregating data from several sources. As we come to the end of our journey through the ultimate fate of the universe, we ask you to think about how big and mysterious the universe is, and how each new finding helps us better understand our place in this constantly changing web. The study of cosmic evolution, from how galaxies form and how dark forces interact to the dramatic events that could one day bring the end of the world, makes us think about time, matter, and life itself. Every new idea not only helps science move forward, but it also leads to new tools and ways of doing things that could change the future of life and society. If you like this exploration as much as we did, please subscribe for more deep dives into the secrets of the universe. You can also leave a comment with your thoughts or questions and share this journey with other people who are interested in the universe. Your participation helps us keep learning more and makes it possible for us to find the answers to the universe's mysteries, one discovery at a time.